We started this learning sequence thinking about how we could get electricity from a magnetic field, and that's what led Faraday to discover his law of induction. But now let's look at the actual device, at an electric generator. And there are many kinds of amazingly complicated electric generators. We're going to imagine the simplest one. So here are the poles of a magnet. They're sitting there just to give us a nice uniform, well, it wouldn't be perfectly uniform, but some magnetic field in between B. So we have a B field in this gap in the magnet, and inside we put a coil of wire that we can rotate. So this is a wire loop, and it can spin about this axis. So as it spins, its area vector, A, will rotate in between the two magnets, so the vector A will rotate with respect to the magnetic field direction of B. So if we rotate the loop in a uniform B, then we know we will get a d phi b dt. The magnetic flux through the loop will change in time, so therefore we'll get an EMF. So this is how you can induce an EMF in a circuit if this went onto a circuit by rotating a wire loop. So let's look at what we would get. So we know in this case if the B field is uniform and there's the A vector, that the magnetic flux through the loop would depend on that angle theta. We know it would basically be B, the magnetic field B if it were uniform, times the area of the loop times cosine of that angle. So for uniform rotation, theta is omega t. That just means we spin at some frequency omega. If you want to think of it in terms of hertz, it's 2 pi times the frequency f times the time. So all we got to do is plug that into theta, and we get the flux as a function of time, B A cosine omega t. And that's good. It can go positive and negative. As the cosine goes positive and negative, the A vector can be along the B field. The A vector can point opposite of the B field. Everything makes sense. Now let's use Faraday's law and write down the EMF we're going to get. So we know it's always negative, Lenz's law. We usually put an n here if it has n loops, right? So maybe it's actually going around n times. Wire loops, n. I just drew one, but you could have drawn many loops. And then it's d phi b dt. So let's see what that is. That's minus n. And the derivative of this with respect to time is derivative of cosine is negative sine, and we pull out an omega, so it's b a omega sine omega t. So that's our EMF, and then you see that this is an AC EMF. This is an alternating current. Which we know as AC, and soon we'll have an entire learning sequence on AC circuits. But this inherently gives you an AC, an oscillating EMF. You never get a DC EMF out of a simple generator like this. So let's look at one and see if that's really what happens. So here is a very old model of one of these. This may be so old, it may be closer to Faraday than we are to when this was made, I'm not sure. But it is a loop here. And we don't have a giant uniform magnetic field, but we do have a magnetic field. So this is 1/2 of what used to be a nice little horseshoe magnet. So this one is creating magnetic field sticking out and sticking into the loop. So we have a field through the loop. I'm going to rotate this thing, and the EMF induced is going to the oscilloscope. So as we watch, I'll rotate it kind of slowly. As we watch, we are changing the flux. Here we have a large flux. When we're like this, we have zero flux. So as I rotate it, I'll try to rotate it uniform. we'll get a varying flux through the loop, so we should induce an EMF. So what you can see on the oscilloscope is sort of a positive high voltage, and then it goes negative, and then it goes positive, and then it goes negative. And it's switching because we have some area vector on the loop. We can define it one way or the other, but it's one way or the other. So in one direction, the change, the area is going into the field, the other it's going against the field. That's why you get positive and negative. If I spin it faster, you'll get a bigger effect. It'll come together more. You're seeing really sharp spikes. That's because these always require, when something is spinning, and then you have to have electrodes on it, there always has to be some contact. There always have to be these brushes for this kind of a setup, and those lead to those spikes. So don't worry about the spikes. But there you can clearly see the EMF forming that we've been talking about. And you can see it's not a perfect sinusoid as we describe here, but that's because this setup is not ideal. Okay? What do you do with it? So we've made an EMF. Who cares? What we really want to do is use this to really drive power in something. You want to put a load on it and make it into a real device. And here's an example of that here. Some clever person, I found this in the demo room, has taken a pencil sharpener and somehow stuck a magnet on it and used the inner workings to generate an EMF and then hook that up to a light bulb. So here you can see, as I turn the pencil sharpener, the light bulb lights up. And you can even see that it's AC. You can see the little filament flashing with some frequency. And the faster I go, the more power we generate. Okay, so now let's look a little more mathematically at the power and how much we can expect to get out of the generator like this. Let's look at our idealized generator and think about how much power we expect to get from it and where it comes from. And power, of course, I mean the joules per second, how much energy per unit time. So I'll draw it a little bit less realistic, even more idealized, by thinking about a magnetic field into the plane of the board. And then imagining our loop, I'll draw it in the board like this, like that, and then it goes to a circuit with resistance R. Everything else is the same. It has area A, this is B, and somehow this whole thing is going to rotate at omega. So how much power will be dissipated in the resistor? Well, at this point you can treat it very similar to how we thought about DC circuits. We know that you're going to get an EMF that we already calculated, the EMF. It's going to be applied across the resistor, so the power is, in a DC circuit, it was IV, it was I times the voltage across the resistor. Well, here it's just I, the current that you get, times that EMF. You're putting that EMF across a single resistor, so it's pretty much that simple. And you can also use the same substitutions. We said it was the I times the delta V, or in this case, I times the E. You could also write that as E squared over R, because E equals IR. If you wanted to get the current, it would just be the EMF over R. You could write it that way, or you could write it as I squared R. It's really just these two equations being combined in different ways, just like it was for the DC circuit. It's usually good to use the one where you know all the parts, right? We haven't calculated the current before. We could. We haven't. So let's just go with the EMF and the resistance that we were given, even though we could easily get the current if we wanted to. Okay, so P in this case would be, let's see, the EMF squared is basically every one of these factors squared, N squared, B squared, A squared, omega squared, sine squared, omega T over R. That's basically it. So everything there kind of makes sense. If you had more coils, you'd get more power. If you had a stronger B field, more power. Bigger loop in the generator, more power. Go faster, more power. It should always be positive. Good. Thank goodness we squared the sign. It'll always be positive. But look here at the R. So if we just have this thing rotating, this is all steady, right? Or it's steadily rotating at omega. This is all the same. And you go and you start changing R, it looks like you're going to change the power. So often it's called the load. R load. It's just whatever system this generator is working on. So you'll see load a lot in electronics. So if we have smaller R load, we have more power. So this implies that this thing is just sitting here spinning. It doesn't have a set amount of power it gives out. It's going to depend on the load. And that is actually true. But let's now go back and look at the mechanical thing that's doing the spinning. So let's think about the torque at the end doing the work, the end that's spinning. So let's draw our loop at some angle with some area vector like that sticking out, and it's in a uniform magnetic field B, and we know it has to be rotating at omega. So at this moment, the phi, the magnetic flux through the loop, is increasing. Because A is turning, I said it's turning this way, A is becoming more aligned with B, it's going to have its maximum flux once the area vector and the B field are aligned. So we can think about what's going to happen in this case. Well, we know Lenz's law wants to oppose the change. So Lenz's law wants to create a bigger flux the other way. Therefore, it wants to create a magnetic field the other way. So current is going to flow to make the field, to make a field back. So that would be current flowing, according to the right-hand rule, this way. So we're going to induce a current in this loop, is what really is going to happen. The direction actually doesn't matter. We're going to do the rest just with magnitudes. But let's note that the induced current feels a torque in the external magnetic field. So this thing is a current going around a loop. It has a torque, or it has a magnetic moment, IA, and it's in a B field. It'll feel a torque, just like everything we talked about in the earlier Horning sequences. So that torque, it's actually in IA. So in means I just drew one loop here. I could have n loops. It doesn't have to just be one. So the magnetic moment of a loop is in IA, just in case you have multiple loops. So we'll go ahead and write the n just in case there's multiple loops in there. And then for the torque, it's that mu. This is basically mu, the magnitude of mu, crossed with B field. So we'll just write it as B, and then sine theta. Theta is the angle between them, but we know theta is omega t. So we'll write sine omega t. So that's how the torque will vary in time and with all the amplitudes. Now the power, we want to get from the torque to the power. So to turn it, we're having to overcome this torque. We're having to apply the opposite and push back. So the power that it takes to do that is actually omega, how fast we do it, times the torque we have to overcome. And the reason is similar if you want to think about pushing something in a straight line. You know, when you push, you apply a force along some path. The work you did was force integral of f dot dl, or just force times distance. The power you did depends on how fast you pushed. So you just take the distance per unit time, that's f times v. Right? So the power when you're pushing something steady is just the force times the velocity. Here it's similar. If we wanted the work we did to push against a torque, it would be the torque times the change in angle, times the how many radians we turned it. Or if you want the power, it's just that angle per unit time. So that's omega. Right? So power is torque times angular velocity. Okay, so now let's start plugging in and see if we can get the power. Let's see. So the power that we would have to do to make this happen is omega times NIA. Let's see, so N is just N. And then I, we're going to get from our previous work. So the current we calculated before, based on induction, was the EMF over the resistance. So the EMF was NBA omega sine omega t. That was the EMF divided by the resistance R would be the current that you're going to have at any moment. And that's just I. Now we need AB sine omega t. AB sine omega t. All right, so let's put all that together, and we get that the power due to the mechanical work we're having to do, is n squared, a squared, b squared, omega squared, sine squared, omega t, all over the resistance R. And you can see that's the same thing. I kept it as we had here, n squared, b squared, a squared, omega squared, sine squared over R, over the load resistance. So it's true. If you're just turning a transformer against some load, if the load changes, the amount of power output changes, but also the amount of work you have to do changes. So there are many, 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 many more complicated transformers out there. I'm just showing you the basic AC transformer, just to give you the idea. We would have to do many, many courses to describe all the different transformers. Motors are sort of the same thing in reverse. With a motor, go to the other end and do some work on the electrical side, and you can produce a mechanical motion. All very similar equations. And then again, there are many, many different motors, so you can drive them with AC instead of DC. It's a whole world of information out there. But now that you have the basics, you'll be able to follow it.